you don't mind?
Sure.
I'll hit record, and it looks like you say 11B, a conceptual question?
Yeah.
Okay.
Yeah, so I've watched your video because you already made a video on this problem. So I've watched it and I understand what you're doing, but there's something I did, my initial thought was different and it's not right. And I'm just curious as to what I'm thinking about wrong.
Oh, okay.
So I guess I used energy to find that equation, for velocity as a function of position. So like.
Okay, good. Yeah, that's my first question. Did you use energy or did you use, kinematics? You did energy. Okay, good.
I did energy and I got, the root of k over m times a squared minus x squared to the 1/2.
Okay, yeah.
But then I was curious why, for finding acceleration, I can't just take the derivative of that equation to find the acceleration with respect to position.
Careful. Yeah. How do I say this? When you say take the derivative, don't forget derivative with respect to
x.
Well, no, derivative with respect to time is acceleration. You take the derivative with respect to x, you're not getting acceleration.
Right. Okay. I follow. Okay. Cool.
Yeah, so you're right. You're right that you can take the derivative, but it has to be with respect to time, not with respect to x.
Gotcha. And there's no t in that v with respect to x equation, so it wouldn't really do anything for me to take the derivative with respect to time.
Well, it would be hard, but I think you could still get something out of it because now remember x is a variable of time, so you could treat x as a composite function, so you could then have, you've got an x squared in there. So when you take its derivative, you would have 2x dx dt.
Yeah.
And then you could write the dx dt as velocity, and you've already done velocity. So you could put in the x, you could put in the velocity, and then get the acceleration. So it seems like it could be done.
Okay.
If you remember that it's, two things. One, it's a derivative with respect to time, and then two, your x is going to be a composite function, which will leave you with a dx dt, but you can put a v for that, and you've just done v. So
okay,
it's not wrong. It's just
seems a little harder than it needs to be. Your solution was certainly simpler.
Yeah. And that can be said a lot. It seems like I did a lot of that for the group in 121 that we talked for about an hour with last hour, and there was so many different approaches. And even in the first discussions today, I even asked people, what do you want to go this way, or you want to go that way? Do you want to call it a sine? Do you want to call it a cosine? So it's, I don't know, having multiple ways sometimes is even worse because it's like, I don't know which way I want to go. I got too many options. Just tell me what to do. But but what I find fascinating about all these problems is there's usually multiple ways to doing them. And your approach would be certainly a normal, if I can. It's not normally done that way. But as I think about it, I'm like, well, yeah, it could actually be done that way, and that'd be interesting. And so I'm even tempted to, maybe tonight when I'm sitting around looking for something to do, I'll go,
see what happens.
I'm gonna take derivative out and see what happens with the chain rule, and put in velocity, and it'll be kind of a weird way of getting there, but it should get there. Because you really have more. It's kind of like you would have an implicit equation instead of a explicit equation, but it still works.
Okay, cool. Thank you.
Yeah. All right. Oh, I forgot to mark down what time I started. That's probably about 2 minutes ago. Now I'll call it 3:07. All right. So we started at 3:07. So it's now 3:09. Let me let's get to the second question here in the chat room. 57. I don't think I've seen that one yet. Okay. So chapter 15. Number 57, and this would be at 3:10. Okay, so let me jump over here. And I think I was successful in updating my computer. I If any of you were here in the first session, I think some of you were. It crashed a few times, and I've discovered why. At least I think so. Not turning my computer on for a couple of weeks here, or at least my laptop. I didn't have their update, and so I was trying to update while I was trying to Zoom and was having troubles. Anyways, but on the last, so I updated it on the first break, and then after I got done, it said it needed more updating, so I updated on this break. So hopefully the two updates updated each other. All right, so let's go here, and I'll write in case anybody's just kind of scanning the video feed, they can see chapter 15, number 57, page 1, and 57. Oh, yes, this is a great one. A horizontal plank of mass M, length L, is pivoted at one end. The plank's other end is supported, and this is going to be a rotation, so torque's going to be important. So where is that spring? The other end is supported, so the very end of it, supported by a spring of force constant K. The moment of inertia of a plank about its end is 1/3 ml squared. They were helpful there. We didn't have to go back and look that one up. Okay. The plank is displaced by a small angle theta from its horizontal equilibrium and released. A. Show that the plank moves in simple harmonic motion with an angular frequency given by. All right. So I'll use this as an opportunity to kind of summarize what you hopefully got out of all the lecture, and then I prefaced it in some of my video solutions, that if you ever see an equation that looks like this, okay, second derivative of the function, and it has a negative, well, maybe something out in front, and then that function back, that solution is, and maybe I'll just say the stuff out in front is box. The solution to that, so x would be some amplitude, and then cosine, and it'd be square root of box multiplied by t and some whatever phase, depending on how you initiated the movement here. Okay, and that is simple harmonic motion. And so the key to many of these problems is to go back to our mechanics, and if it's a translational problem, do the sum of the forces. If it's a pivoting or rotating type of problem, we do the sum of the torques. But the key is to try to come across an equation that looks like this, because then we know the answer to it. And this little box then, and the square root of that, so the box would be what we're calling omega squared, okay? And when we did a spring, we got the spring constant and the mass there. And so we just said omega was the square root of k over m. And that's the first one we did. But some of these harder problems like 57 and 63 and the next one, is that 67, you know, those are harder problems. 55. All of these fit in that same category where I'm going to write out the forces or the torques and come up with an equation like this, and then that's how I'm going to find the omega. So that's what this question is saying. It says, you know, show that it's harmonic motion. So okay, if I have that, that's showing it's harmonic motion. And angular frequency, so I can just take the square root of whatever's out in front. So that's my goal. That's my thinking. That's what the big idea of this chapter is. So for this specific problem, I'm going to do something like this. And maybe I'll make a series of 3 pictures, because maybe the first thing is that I have a spring mounted vertically at its natural length. Oh, I'm sorry, I thought I heard somebody talking. Okay, and then I have a plank And I'm going to start with the plank not in contact with the spring, okay? So this would be my x equals to 0. And as a comparison, I did the same thing when we made a vertical spring. I just said, look, let's, hang the spring, and that will be the natural length of the spring. That'll be the x equals to 0. Then what I did is I hung a little mass on it, and that extended it down by what I called x naught. And then I pulled it beyond that to let it go. And so this extra distance down was x1. And so it was x naught plus x1, which was the total distance the spring had stretched. So I'm going to do the same thing here. I'm going to first lay the plank onto the spring and just let it rest there. That's going to compress the spring a little bit, call it an x naught. And just like we saw for the vertical spring, ultimately the x naught doesn't matter. I'm going to hopefully prove that to you here, that this initial compression due to the weight of the spring doesn't matter. But I want to make sure you realize I'm considering it. Okay, so then my third picture is to say, let me just kind of like put my finger on it and push it down a little bit more, or pull it up. Maybe I'll just push it down a little more. Push it down a little more. And that means it's going to go down even more. Let me call that x1. And maybe in this picture, I'll call x naught. So once I let it go, the whole spring has been compressed by a total of x naught plus x1. So again, no difference than the vertical spring. In fact, almost everything is identical to this, except since we're talking about a pivoting problem and a rotating problem, this problem I'm going to be doing the sum of the torques, whereas the vertical spring I did the sum of the forces because it was a translational problem. Okay, so this is the page 1, if you will. Okay, so here on page 2, as I said, now if I apply my Physics 121 and say, all right, let's add up the torques. And so the sum of the torques equals to I alpha. And maybe over here, I better do the free body diagram. And so the free body diagram looks something like this. And of course, the center of mass would be right in the center. So there would be the force of gravity, mg. There would be the force from the spring, and it's going to be right at the end of the plank. Let me just call the plank length L. And so the phrase I like to use from Physics 121 is take the force of gravity and everything touching it. So the spring's touching it, but so is the wall here. And so oftentimes we label these forces from the wall as the reactionary force. So R in the Y direction and R in the X direction. And that's the two things touching it, the pivot point on the wall, the spring, and then of course the other force is the force of gravity. So when we go to add up all the torques, then we'll do the torque right here where it pivots. And again, just as a remind you of Physics 121, the reactionary force then is 0 torque, because torque is this R cross F. which in terms of magnitude would be RF and the sine of the angle between R and F. I'll call it a phi. Because some of these problems can have multiple angles, and phis and thetas always get confused. And I'm going to use a theta real soon, so I want to call that a phi. And sometimes phi and theta can be the same thing. Sometimes they can be different depending on what we mean by them. But this angle, whatever we call it, theta or phi, is the angle between these two. And I'm going to call it a phi. So this is the angle between them. But the point here is, in case you had forgotten from 121, is the torque you get from these reactionary forces is 0, because you would put in an R distance of 0. And so when I say add up all the torques, the good news is I don't need to worry about all of this. I just have these two to worry about. Okay. So I will then say sum of all the torques. And I'll say there is a torque from gravity, so I'll call it T sub G. And then there is a torque from the spring, so I'll call it T sub S. All right, now the torque from gravity using this equation would be the distance away. Okay, so this would be L over 2, if we're talking about the whole plank being the length of L. The amount of force is mg, and it would be sine of, now this is interesting, because if I extend it out, it's an angle of nearly 90 degrees. But maybe not exactly 90 degrees. The way I drew it, I kind of drew it as if it squished it down, so it was 90 degrees, but it could have been angled up. So even though I put a right angle here, maybe I shouldn't have done that. Let me call this theta. And do I want to do that? No, because I already did a phi down here. Let me call that a phi, because that's what this one would actually mean. This is the angle between them. All right, so that's sine of phi, which, as I said, may or may not be 90 degrees. Okay, but more on that to come. Let's talk about the torque. Oh, and I guess I should keep an eye on the sign of it. Let's see, gravity would be pulling it in a clockwise direction. And normally we call clockwise a negative motion. So I'll stick to that tradition and put a negative torque there. Because remember, this formula here is the magnitude of it. We have to either look at the picture or do our little right-hand rule to get the direction of that torque. So I'm dealing with torques. And I'll say it again, this is one of the challenging, I think, parts maybe of this chapter is it's going to rely on 121, which for some of you is, a year ago. So this is a good review.
Yeah, no, I was in 115 last year, and this is like the whole semester.
Yeah, okay, exactly. Yeah, the whole semester is about static equilibrium. Yeah, right. Yeah, so there's that. All right, so that's easy for you. All right, so then the torque from this one would be, and I'm going to go through the same logic. It's the distance away, so that's L. And when I say distance away between the force and the pivot, okay, so there's L. The amount of force is the force from the spring, and I'll just do absolute value. So I'll put Kx. We'll put the minus sign, because again, this formula is absolute value, so this should be the absolute value of the force. And then it would be the same idea. It would be a sine of phi. Okay. Now, here's where some cleverness is going to come in. Oh, maybe I should do direction before I leave, but the spring's pushing up at, well, spring's kind of confusing because you pull down and it goes up and you pull back. So maybe what I should do is something like the following. Maybe I should put a negative here. And then call down on the spring negative so that as I compress the spring, that negative with that negative, of course, makes it a positive torque. Yeah, I think I'll do it that way. But here's really what I wanted you to see here. Okay, so this first term, let me leave alone. So negative L over 2 mg sine of phi. And then negative the L Vk. And this is why I went through this 2 steps here. This would be x naught plus x1 for the total distance. We've compressed it. And this first term, minus L over 2 mg sine phi, together with, and I'll multiply this out into 2 terms, the L, the K, the x naught, the sine phi, and then minus the L, the K, the x1 sine phi. These two, and it may not be so obvious yet, but those are 0. See, those are the two, let me come back to my picture. Those are the two where in the second picture I drew said that when the spring compresses down x naughts, it is just enough to balance the torque I get from gravity. And so what I was saying here is that the torque is 0 at this point. That is gravity pulling it down and the spring, just the x naught amount. Now, when I pushed it down a little bit more, this is what makes it a little bit greater and makes it snap back up. But the x naught part of it is just enough to balance it. So we can just say whatever those numbers are, we don't need to worry about them. We can just say those come out to be 0. So this comes out to be a minus LK x1 sine phi. And I will say it that by analogy, I did that same thing when I was doing the vertical spring. That's why I broke it up into an x naught and an x1 so that we could argue that the initial stretching of the x naught balanced the force of gravity. Those go away, and the only thing you have left for a vertical spring is the extra x. There, you don't even have to worry about gravity. So even though a vertical spring is vertical, we often don't have an equation that has gravity in it because what we would call maybe the extended equilibrium has balanced it off. And that's what I'm trying to say here. The compressed equilibrium, if we start and consider that as our reference point, so we measure x1. We don't measure the total x of the compressed spring. We measure just the x as measured from the equilibrium point. Then we have a very simple equation that doesn't even have the force and torque of gravity involved. And that's a big part of this problem, believe it or not. Okay, now I think it froze because I don't see my hand or my pen. As I say, let's go to the next page. Well, that's a bummer here. All right, so let me stop sharing here for a second and reconnect my crazy phone. Let's see what I got to do here. So I go to share. And screen sharing. And give that a second to kick on in. Still spinning. And meanwhile, I'll just go to page 3. There it is. Up.
Yeah, it's working now.
Okay, good. All right, so let me put page 3 here, but let me move it so you can still see the bottom of page 2. So it was this equation that we got the torque. All right, so let's continue on with our mechanics. The sum of all the torques is equal to I alpha. Okay, so now we have the torque. We said that the net torque would be minus LK and X. And if you don't mind, I'll go ahead and just now call it X. I know in here I called it X1, but if you let me go back to the picture, let me just call this X from here on out. And so we're going to measure everything from the equilibrium when this weight of the plank makes the spring balance. Okay, so I'm just going to drop the symbol X1 and just call it X. So everything is measured from the equilibrium position. All right, so let me not forget the sine phi. Okay, now the other side of the equation, maybe I better come back to the picture, is the I alpha. Now, looking at all of these pictures, you'll see that this is a plank that is pivoting around its endpoints. And I wouldn't expect you to remember that it's 1/3 ml squared for the moment of inertia. In fact, they even give it to you in the problem. But I guess I would expect you to say, okay, we can go back to chapter 10 and look at that little chart that lists all these. So I'm going to put in 1/3 ml squared for the moments of inertia. Now, the alpha is the second derivative of the angle. And this is where I want to be real careful. The angle, this is where it pivots. And so it can go up and it can go down, but this is the angle theta. So theta is measured how it pivots. Do not confuse that with the phi. That's why I wanted to use a phi here, because phi is the angle between R and F, but theta is this angle that it pivots from. And so that's why I wanted to make sure I used a different symbol, because the angle for the torque and the angle that it pivots are two different things. Now they're related, and so we're going to have to figure that out, but those are two different angles, and so that's why I picked the phi back here. Now, in fact, we're going to play the same game we did for the pendulum and for some of the other examples. Let's just say that the amount of pivot is kind of small. We call this a small angle approximation. If you remember from the lecture, sine theta is approximately equal then to theta if you're willing to be in radians, and if you're willing to say less than about 1/2 a radian, which is approximately 30 degrees. So coming back to our picture, if you say you push on this and you angle it down, but less than 30 degrees, and that's still a pretty good movement. If you're willing to do that, then you can roughly say that everywhere you see a sine theta, you can replace it with, say, theta. Now, I'm not sure I see a sine theta yet, but it's coming. Watch this. Kind of in the same agreement, if you push this down a small angle, you're still looking at an angle that is probably pretty darn close to 90 degrees. So I'm going to say that the torque from gravity is always something pretty close to 90 degrees. And then the torque from the spring is pretty close to 90 degrees. Here's why that's relevant. I could just say, well, it's near 90 degrees. Exactly, no. So if you wanted to do this a little more accurate, you'd have to kind of consider that. But I'm going to take advantage of this later on anyways. So for this to work, I've got to say that one really doesn't change. So sine of 90 degrees, of course, is 1. So we could pretty much say that if you're going to push it down a small amount, oh, why did I put a half here? Sorry about that, 1/3. Okay, but the moment of inertia, 1/3 ml squared. And so this maybe is best to say approximate. Maybe I shouldn't put equal here. Maybe I should put approximately that, because I fudged it a little bit. I said, look, I'm not gonna pull it down too much. But here's the important part of that, is this x. Because if you go all the way back to the beginning where I started this problem, we're looking for equations that look like this, that whatever you're taking the derivative of twice is shows up in your equation. And you can see that I am taking the derivative twice of the pivot angle. And that actually shows up right here. Let me kind of do an object that pivots. I'll give it a little arc, but we're treating this as the x. But if you remember from your math class, usually an arc length we called an s. Oh, and I guess you also did this in Physics 121. The arc length is the radius times this angle. And that would be that pivot angle. So if I call that pivot angle theta, which I have been, then this arc length is this s, which is pretty close to that x. And the r is the length of the plank. So I would say that x is the length of the plank times the angle. So I'm going to put in place of x, L theta. And that is really an important step, because now you're seeing that I have a second derivative of theta, and it's equal to then the theta. That's the kind of pattern I'm looking for. That's the kind of pattern that would give me simple harmonic motion. Now, as long as I'm here, I might as well cross out an L squared and an L squared. Now, I already have the negative, so I'll continue with that. There's the K from the spring constants. Let me bring the 3 over, so it's 3K. Let me divide by the mass. There's theta, and there's the second derivative with respect to theta. And that's the magical step. I'll go all the way back to the beginning here, right? We're looking for something that says if you have the second derivative of something, and you end up with a negative and whatever this box is times x, that box is omega squared. That is, take the square root of that box and you'll get omega. So this says that omega would be the square root of this thing. It would be the square root. So not counting the negative and not counting the function, it would be the square root of 3K over m. So the fact that I end up with this equation is proof that it's simple harmonic motion. And then the square root of the things out in front of the theta, not counting the minus sign, is the omega. And that's what let me double check. So it says, show that the plank moves in simple harmonic motion. Okay, that's what that equation is. With an angular frequency of, check, square root of 3K over m. So that's our proof. Now there's a part B. Part B says evaluate the frequency taking the mass to be 5 kilograms and a spring constant. Oh, so this is more of a plug and chug, but I'll do it. So omega is, so 3, and then a spring constant of 100, and a mass of 5. 5 goes into 100 20 times. 20 times 3 is 60. So this is the square root of 60. So square root of 60 is then 7 points, we'll call it 7.5. Now that's the angular frequency, so I don't think that's what I want. Let me come back here. Evaluate the frequency. So I think they want the linear frequency. So remember that 2 pi f is the omega. So f is the omega divided by 2 pi. Okay, so I got to divide this by a 2 and also divide it by a pi. And so this would be a frequency of 1.23 hertz. Yay! Suppose I should check the answer on this, but that seems pretty straightforward. Just plug and chug into it. So I forget what number this was. 57. Let me scroll down. Okay, so they did all that and got the same thing I did, and then yeah, and then the same frequency. Yeah, good. Good, good, good.
Okay. Okay. I see. My critical mistake was not realizing that when it's at the equilibrium, the two cancel, and it just leaves you with that third term of the equation you have.
Yeah, no, I admit that's a bit tricky. And then of course the author was, and myself, to be honest, when I picked the problem, was kind of expecting, okay, that's going to be the tricky part, and you get that, parallelism between what I did for the vertical spring. So it was kind of testing you to see if you would do the same thing. Okay, well, now you know it. So now on a test, you'll do it. Get 100%. Are you in dynamics too? You said you did statics. Did you do dynamics? Yeah, so
it's just physics 121 with like new symbols. Thus far.
Statics is, yeah. Well,
No,
and dynamics.
Dynamics is like, it's just kinematics.
Yeah.
At the moment.
Yeah, a little harder problems though.
Yeah.
And I said that because you did things last semester that were, again, just in a static situation. And that was the first part of this. But you'll do a problem like this, I'm sure, later on in the semester where now that it was in equilibrium, you push it down and it vibrates. And you'll go, there's probably a chapter in your statics book on harmonic motion. So
yeah, I'm sure.
Yeah. Okay, so let me click back over to the chat here. All right, so that was 57. All right. Quick question 17.
Yeah, I don't think you need to write stuff down for it.
Oh, okay.
So when I did the problem, I just did 50 grams in the calculation, and then I checked my work for part B and noticed that they put a milli with the weight. So I was just wondering where that 10 to the -3 came from in part B in the calculation.
Let me see here. Let me jump over. Okay, I gotta see the question. So 17. Oh yeah, so they say 50-gram object. So you total some. Okay. So I see the 50 grams. Let me jump to the solution. So you say in the solution, which A, B, or C, which is it?
Part B.
So part B.
They put a milli with the 50 grams, which I didn't see anything in the question that indicated that it was.
Oh, no, because they're okay. Oh, yeah. So they're putting the mass in kilograms.
Okay.
Yeah, so 50 grams is 0.050 kilograms, which can be written as 50 times 10 to the minus 3 kilograms.
Okay.
So they're
And
just trying to make sure they're putting in the mass in kilograms. I think this would have been a better and less confusing approach.
what's the reasoning behind that? Why can't you just leave it as 50 grams?
Oh, let's see why. Let me go to the line before it. The velocity, the equation for velocity is the omega square root of a squared minus x squared. This is in units. Okay. So then So then they're going to go omega, which is the square root of k over m. And here's the key. They put in the spring constant of 35, and 35 is newtons per meter. And
Okay.
inside a newton is a kilogram meter per second squared.
Oh, I see.
So you got to make sure that your mass, matches. So I think what you're getting at is, if the top was done in grams, I could have done the bottom in grams. Yes.
Okay.
But once I do the 35, which is in newtons, which has kilograms, I'm required then to make sure the bottom is also in kilograms.
Yeah. Okay, that makes sense. I just forgot that newtons has kilograms in it. So, yeah,
Yep.
that explains a lot. Thank you.
Yeah, I feel like we're doing a lot of Physics 121 today, so maybe it's a good review for all of us.
That seems like what chapter 15 is just more complex Physics 121.
Well, sure, and you can see where it is in the book, right? So Physics 121 did chapters 1 through 14, and then so the next step is this. I mean, this is just a natural next step right after chapter 14.
Yeah.
And it's right. So where I would still say we're doing mechanical stuff. Now, for some of you, and you included, you jumped into last semester where you did all this electricity and magnetism stuff. And once we start doing that, what's that you, Daniel? Yeah, you were. Yeah. So you did a lot of 122 stuff, and in that we were doing things that weren't mechanical. So seldom. Well, that's not true. There was a lot of times we bounced back when we had electrons moving. So I was gonna say we didn't do a whole lot of 121, but that's not true either. It shows up all the time.
Okay.
Anytime mechanics is going on. Yeah. Oh, nice. All right, I'll jump back over here to the chat room, and let's see. Yeah, I don't have anything from you guys. So anybody wants to chime in or type something, we'll do something. It's starting to get warm in my side of the world. I think I mentioned this before, but it wasn't since last October when we hit that heat spell. My outside wall and window is on the west, so I'm good in the morning, but I hit that afternoon and it just starts getting hot on this summer day in January.
I walked outside my house today and was sad winter was over.
Yeah, it's like, whoa.
Hopefully we get a little more rain before it just all summer starts again.
We haven't really gotten any rain.
Yeah.
I did see 50%.
It was it only rained once, right?
Yeah, it's like one storm. It rained a lot in like
I wasn't even here for it.
It
First time
rained 2 times in my hometown, which is an hour north of Santa Barbara. So
it's literally only rained one time in LA, like this entire winter season. Like it rained one day on election day, and then like once like 3 weeks ago, and that's it.
Wow. Yeah, it rained about 2 inches at my house, which was significant in in Carpinteria, you know, about a couple weeks ago, you know, when there was that rainstorm that came through, and nothing since.
Yeah. Although as you guys are talking, I'm looking at the weather. It looks like we got a 50% chance of rain on Friday.
So basically no rain.
Yeah, probably still no rain. It's only a 50% chance. Although
I've seen it where it's been like 90% chance and it still never rained. What I don't trust weather people anymore, because I'll be like looking forward to rain and there will be no rain.
Yeah, it's such a hard prediction. Weather and climate are so very complex, intertwined together. So, although a lot better than it used to be. When I was a kid, I mean, literally, the weather the next day could just be totally wrong. I mean, at least our models are something good. Like, you know, they say, well, you get, you know, they give you an 80% chance of rain, so it doesn't rain, but at least it looked like it was going to rain. At least it was going to be cold. At least you know to put on the sweatshirt, you know.
Mm-hmm.
Well, when I was a kid, they'd say 80% chance of rain, and then you'd have a day like today. It's like, really? Not a cloud in the sky. So their models are a lot better.
Yeah.
All right. Oh, looks like I was chit-chatting. You guys shot something up here. Okay, so let's go on to another one. Let's see, where were we? We just did kind of a, that was Daniel. So Anthony, how about number 63 from chapter 15?
You know what,
Yeah.
There's like that 63, I imagine will take a long time. So if the other guys want to go first, that's fine.
I'm actually interested in 63 as well, though. So.
Oh, okay.
Oh, okay. Oh, and you asked the next one, Leonard. So, all right.
Yeah, and if we want to get to the 121 afterwards, I totally get that. So.
Okay. Oh, thank you. Yeah. Yeah. Because it looks like Dylan popped back in here from 120. So let me do the 120. Let me do your 63, but then I'll jump down and do Dylan's, and then get back up, Hunter, and do yours. Okay.
If there's no time, that's also good. I'll be here next Friday.
Oh, okay. Well, don't worry about time. What time? Oh, we still got a lot of time. Plus, I'll just take whatever time need be. I don't want to leave you guys hanging. Okay, so let me put here chapter 15. In case, like I said, anybody's scanning, I'll put number up top. Page 1. And about 353, I'll start this one, okay? And jump over to the question. Good. And I'm going to say the same thing here on 63 that I just said on the one before that, which I guess was 57. Keep in mind this, that if you ever see an equation that looks like this, okay? Second derivative of position with respect to time has a negative, and then something. We'll just call it box, and then that something again, then the solution for the position would be some amplitude cosine of omega t plus phi, where the omega is the square root of that box. So ignore the negative in the function, and that would give you the omega. And of course, the phi is determined by how you initiated it. Did you push it up? Did you push it down? Did you tap it? Okay, so we got to kind of look at the physical picture for that. Okay, so this one here, we have kind of this horizontal line, and we take an object here that has mass m, and we tie a string on both sides. I'll just say pretty tight. But then we lift the object off center and let it go. And if you've ever seen something like this, you can kind of imagine it just kind of rattles back and forth, up and down. And so this one says a ball of mass M is connected to 2 rubber bands. So we've got a rubber bands of length L, each under a tension of T as shown in the figure. The ball is displaced by a small amount of distance, y, so we pull it vertically a distance of y, perpendicular to the length of the line. Assume that the tension does not change much. Okay, so technically, you pull it up here, this rubber band is stretched a little bit, but let's just call it T, and it will be roughly T because it doesn't really stretch by that much more. And so assuming that the tension doesn't change, show A, that the restoring force is. Okay, so let me go to the free body diagram. And so here's this object. And if you look at the restoring force here, I would have the tension pulling this way. So let me call it T. And I would have a tension T, pulling it that way. Now, in case you're wondering about the force of gravity, let me say the same thing quicker than I did last time. I'll pull up my notes from last time. But the last problem we were doing, 57, remember this discussion that the weight of the plank was balanced by the initial compression of the spring. And just like we did with the vertical one, we can eventually ignore all that. And so I proved it to you in the lecture part, and the author did too for the vertical spring. And then we just did it in 57, where we don't have to worry about the force of gravity anymore. I'm going to go ahead and just then say, for this problem, let's just jump right to that chase and say, look, when it was at equilibrium, the tension in the string and gravity would kind of balance off. And so what I have is this restoring piece of it. And so let me just draw that without the effect of gravity. So then if I make a grid, calling this the y-axis and the x-axis, so kind of the traditional grid, and I've got a tension this way and a tension this way. If I were to call maybe this small angle here theta, then the x component would be the tension times cosine of theta. And the vertical component would be the tension times the sine of theta. Same thing over here for this tension. If this is the tension, this one here would be the tension times cosine of theta. And this one here would be the tension times the sine of theta. And again, if I do my physics 121, if I add up the forces in the x direction, I get a plus and a minus. So I get a plus t cosine theta and a minus t cosine theta, and that equals 0. And that's maybe even obvious and boring and didn't have to write out. This thing's not going to move in the x direction. But it's the y direction that's of interest, because this one would be a t sine theta in the negative direction, and the other one would also be a t sine theta in the negative direction. And so the total force in the x direction is, of course, negative 2t sine theta, and that would have to equal to ma. Now, keep in mind what I said at the beginning of this problem, which I've said in the beginning of many problems. We're kind of looking for something like this. Something that says the second derivative equals a negative and then some constant and then that function back. And we're kind of along those lines. Here we have the second derivative of position. This is the acceleration in the y direction. I think we need to go to another page here. And so right here, copying down this equation, I have this negative 2t sine theta equals m, and then this would be the second derivative of y with respect to time. So that's the acceleration in the y direction. So it would be nice if I can get a y over here. And I think I can, because coming back to this angle and back to this picture, I was calling this theta, that's what I put here, but that would be the same as this theta. So if you kind of look at sine of theta here, it would be this vertical distance, which is the y, over the hypotenuse, which is the L. Now, I suppose in the diagram, you might say the horizontal distance is L, but remember they said, go ahead and just assume it's pulled up a little bit. And so there's really not a change in the tension, and there's really not a change in those lengths. Oh, and crazy thing froze again. What is it that makes this thing freeze? I wish I knew. But nonetheless, let me reconnect. So things spinning around here. Spin, spin, spin. There we go. We'll come back. Okay. So what I was trying to say when it froze, it was back in this picture here. The author's picture has the horizontal as L, but the hypotenuse is pretty much L also. So when I go sine and I go y divided by the hypotenuse, I'm going to just call that an L. See, and that becomes useful then right here, where I have a minus 2t, and the sine then becomes y over L, and then an m, and then a second derivative. So you can now see we're getting really close to that structure. I'll put the negative out in front, I'll put the y back here, and so there'll be a 2t, there'll be an L, and I can bring the m over, and that would equal the second derivative. So there we have the form. The second derivative equals negative some constant and the function. So that proves simple harmonic motion. And it also shows then that the angular frequency would be the square root of the stuff out in front. And I think that was the problem for A. The restoring force, oh, I went too far. I actually answered B. The system exhibits simple harmonic motion and has an angular frequency of. So I guess this is actually the answer to B. The answer to A was back here at this step, where I said that this would be the restoring force, the 2ty over L. Just check, 2t over L times y. Yeah. So there's A and there's B. Okay.
Yeah. All right.
Yeah. So there's 63. All right. Let's go to the 121 class. Dylan, you were asking question number 4, and I think I remember doing this one. Oh no, from the homework. I did from the quiz. So this is number 4.
Do you want me to share my screen again?
I do. Just a second. Let me give you permission. And the time is 4:05. Okay, yeah. Let me give you permission so you can. Let's see. How do I do that? I guess I first stop sharing, and then I go to Permission, advanced, all participants. Okay. All right, you should be good now.
Okay. There we go. That's the related rates with the spherical balloon.
Good, good. Let me do a screen grab here.
Okay.
Related rates. Let me copy. Oh, it's a balloon, huh? Nice. Let me paste it into that same document I did earlier. Okay. Good, good, good. And then I'll come back over to Zoom here and share my camera again. That'll kick you off. And then let me turn on my phone here. Let me get my paper organized. How many sheets this will take when the red bleeds through. All right, so this is from 121. It's number 4 from the homework here. And it's a related weight. Oh, a spherical balloon, that's important. It says air is being blown into a balloon that has a volume of, and this is the standard geometric equation, but let me use this as a chance to do a little shout out that if you look in the appendices of the survey book and the OpenStax, I'm trying to remember where it is on the OpenStax. In survey, it's Appendix B. In the OpenStax, I'm not sure which appendix it is, but they've got a lot of math things. And so if you ever need like trig identities, or in this case, the volume, surface areas, there's a whole section on geometry. Anyway, so that would be there. But this problem gives it, so we don't need to look it up. Actually, ideally, you would have committed it to memory, but you probably learned this back in 10th grade or something, and maybe haven't used it too much. But it makes good, actually, you see it a lot in calculus, so maybe you've seen it 150. Anyways, at some instance, the radius of the balloon is r, and the radius of the balloon is increasing at this rate. The volume of the balloon is increasing at this rate. Oh, solve for the variables r. So these are, okay. So now, before I do anything with this, and this is what they, is why it's called related rate, remember a little bit from our calculus. I'll start with an easy one. If I had a composite function, and let me just do something like, well, if I put sine x, that's just a regular function. But if I said x was equal to 3t, then what a composite function is where you take this function and then you put another function in its spot. So the x function is 3t, and I'm putting that into the sine function. In your calculus class, you would have, oh, we froze again. Okay. Screen share. And I'm gonna reboot everything tonight and play with this, but so I was thinking it was the update because I updated everything and during the break thinking that would take care of everything. All right. But apparently not. Okay, so hey. Oh. Did I start my meeting twice? I got 2 Zooms going on here.
You might have, because the Zoom I'm on, there's no chat.
Okay. Okay. That's actually making things crash. So sad that you said that? Okay. Yeah, I got you. My apologies. I tolerated for the rest of the time. And I apologize for that, Ed.
Audio's coming through really weird for you right now.
Yeah, you sound like a robot at the moment.
Okay, do you think I should shut all of them off and start again, and that's going to keep you out?
I understand. You want to start another meeting?
Yeah, I can just start another meeting, for sure.
Okay, sounds good.